Swayam Prabha. Digital India. Educated India.
Welcome to yet another session of Introduction to Aerodynamics. So, for people who are following the sequence of these video lectures from day one, I think for them it is easy to understand the perspective under which I am bringing all these topics one by one. For example, the Kelvin circulation theorem, Bernoulli's theorem, etc. But for people who are watching these perhaps this video lecture in isolation, for them just a few words so that they understand the context under which we are discussing all these things. If we are starting with the discussion of drag on an aircraft, and I said that the drag on an aircraft is composed of the drag on the fuselage, wing, etc. Now, we are zooming into the drag on the wing, and I said that to understand the drag on the wing, we have to first look at the flow field around the wing, because the flow field in some way sets the velocity distribution, pressure distribution, etc., which in turn tailors or affects or creates the distribution of the surface forces on the wing. As you can understand, the lift and drag, the two main forces responsible for aircraft motion. Well, I mean, lift is responsible for aircraft motion, and drag is kind of the price you have to pay. So, both lift and drag can be obtained from the integration of the surface forces. And when we say surface forces, we will see that there are two kinds of forces, the normal force and the tangential force, also known as the viscous force or the shear stress, etc. I mean, force per unit area is considered as stress. So, when I say shear stress, it is the shear force. So, tangential force on the surface of the wing per unit area. If you combine all these things together, integrate it and get the resultant force because of the effect of the normal forces, the shear forces, you get a resultant force, and then of course, you decompose it, as I said, in the direction of the relative wind, which gives you the drag from the surface force distribution, and if you resolve it normal to the relative wind, you get the lift force. Now, coming to our presentation deck here. So, here if you see, this is more or less the distribution of the flow field around a cross section of the wing. As you understand, this is a streamlined shape. We will talk about what is streamlined shape, what is the difference between streamline, what is the difference between a streamlined body and a bluff body. As you can see that the wing has this very typical shape, like a teardrop shape or extended teardrop shape, and it's one of the approaches to make an object streamlined, and we will see the importance of streamlining the shape of an object that is put in that has to interact with a flow field. So, if you have a streamlined body, you will see that the amount of drag experienced by that body can be significantly lower than the drag experienced by a bluff body of say similar thickness, etc. So, at the end of this discussion on drag, I will talk about an experiment, a classic experiment that shows you the difference between streamlining a body, the drag on a streamlined body and the drag of a bluff body, and that we will do when we have studied the avenues of producing drag. So, pressure drag due to flow separation, you will see that pressure drag has that qualifier due to flow separation, skin friction drag, wave drag, and in real applications where wings are finite and you have trailing vortices from the wing tip, something known as the lift induced drag. So, there are four components to in general, if you think of the drag on a wing, you have these four components that play their role. So, once we have done our discussion on these four components, I will talk about a classic experiment. There is a YouTube video where Professor Shapiro demonstrates this experiment. So, I will talk about it. I will give you a link to the video, you can go and watch it. So, this one is a streamlined shape, and the flow field around this wing is created because of the combination of uniform field plus a bound vortex field. So, this we talked about in the previous lectures, while we also talked about the Kelvin circulation theorem and the Kutta condition. Of course, I did not get into the Kutta condition in a rigorous manner. That we will deal with when we talk about the lift portion. So, right now we are discussing everything under the banner of drag. So, for some people it might look a bit awkward that we are putting everything like Bernoulli's theorem, Kelvin circulation theorem under drag, but I think there is no harm in understanding that all these building blocks eventually lead to the analysis of drag or lead to the analysis of lift. So, instead of looking at these tools in isolation and later on trying to figure out where they are applicable, I said in the initial lectures that I would talk about the physical phenomena and then bring in the tools. So, right now to understand the phenomena of drag, I am bringing in these tools like Kelvin circulation theorem, what is that substantial derivative thing when it comes to Kelvin circulation theorem. Right now we are discussing Bernoulli's theorem, and in the last presentation or the last class I had come to the point where I said that the gradient of the total head is equal to 0 if the flow field is steady and irrotational. So, we will start with that point and we will see some intricacies of what happens when the flow field is not steady, what happens when the flow field is rotational, etc., to Bernoulli's theorem. But I am creating a context for students who are coming to this video lecture by itself without having the sequence of videos that many of the other of you are following. So, here we have a streamlined body, the flow field is a combination of the flow field generated by a bound vortex and a uniform flow that creates a pressure distribution. If you know the free stream velocity and pressure, I said that using Bernoulli's theorem you can find pressure or velocity on any location of the flow field. As long as you know either pressure or velocity, you can find the other one. So, if you know pressure at these points, you can find the velocities. If you know the velocities, you can find the pressure using Bernoulli's theorem. And right now we are talking in detail about Bernoulli's theorem, and we will talk about the restrictions under which it can be used, it cannot be used, where it can be used with a little bit of consideration, etc. And you can see that the combination of the uniform field and the bound vortex field, velocity due to the bound vortex field, creates a pressure distribution like this. So, low pressure on the top, higher pressure on the bottom, creating a net resultant force at normal to the relative wind direction. So, you see that this pressure distribution creates a large amount of lift force. However, you see that these normal forces do not contribute to drag significantly, in fact, it contributes to drag negligibly, and in the extreme case of inviscid irrotational flow over these kind of surfaces, it goes to the D'Alembert's paradox, where you get lift if there is circulation, but you do not get any drag. However, in real life you get drag, and we will see that it really is from the boundary layer effect. We have not talked about boundary layer. After Bernoulli's theorem, we will get into the boundary layer phenomena, because to understand drag you need to understand the pressure distribution, hence the velocity distribution, but you also need to understand what is happening in the boundary of these objects. This was Prandtl's contribution, that because D'Alembert's analysis was showing that there will be no drag on these objects. The flow will bend around the object in such a way that if you integrate the normal forces in the direction of the relative wind, you will see that the drag becomes 0. So, if there is circulation, you still get some lift, but there is no drag from the inviscid rotational analysis. And when we do our lift force discussions, you will see that we will spend a lot of time in actually formulating mathematically formulating using velocity potentials and stream functions the approach that D'Alembert and mathematicians of his time were taking in analyzing fluid flow. On the other hand, so the surface normal pressure distribution, or rather not normal pressure, the normal force due to pressure is not contributing significantly to drag, but it will contribute to drag once you have flow separation. We have not talked about it. So, that is why the normal forces are still important in the discussion of drag, because when flow separates over the surface of the wing or whatever body you are talking about, that is when some imbalance of the normal force in the direction of the relative wind happens, and that contributes to a large amount of drag. So, at this point I am saying that for the case where you do not have flow separation, and if you have inviscid rotational, there is no question of flow separation, there is no boundary layer, because unless you have boundary layer, flow separation is a boundary layer phenomena. So, in this case you do not have flow separation, or then the normal force distribution will contribute primarily to lift. However, the normal force distribution will get off balanced if there is flow separation. So, the same normal distribution with a flow separation, you will see will contribute significantly to drag. However, the shear stress distribution on the wing surface will have its contribution to the skin friction drag. Okay, so, drag we said is composed of skin friction drag, pressure drag due to flow separation. So, we mention the flow separation part, okay, because without flow separation the contribution to drag is not significant. Wave drag will show up when shock waves start appearing on the wing surface. So, essentially if your vehicle is flying at supersonic speeds, of course, you have wave drag because of the oblique shocks and expansion fans on the wing. Even when you are flying transonic, so suppose your free stream Mach number is still below Mach 1, but it can happen that the flow over the wing can get accelerated and you can reach supersonic flow velocities, and you can have shock waves on the wing surface, top surface, bottom surface, and we will see that will contribute to wave drag. And then when you talk about finite wing, we will have the lift induced drag. So, you can see here that if tau w represents the local shear forces, and we have not talked about how this shear force originates, but nonetheless we will see that when we discuss the boundary layer concept, this shear force thing will come into we will be able to see where this shear force comes from, but you can see already that the direction of these shear forces are well aligned with the relative wind direction. So, if you take the vector summation of the shear stress into the area in which they act and resolve it in the direction of the relative wind, it almost appears that this shear force distribution or shear stress distribution will contribute to drag, and that contribution goes into this thing called skin friction drag. If you take the resultant of all these things, you get something like this resultant R, and then you can resolve it normal to the relative wind and parallel to the relative wind, getting lift and drag, or for the purpose of other analysis you can also resolve it, it does not matter, you can resolve it along any mutually perpendicular axis you want. So, here N and A relate to normal force and axial force, where normal force is along the normal to the chord line. So, sometimes for some analysis you might need to resolve the resultant force R in some different way, and here we are resolving it in this N and A is parallel to the chord line and N normal to the chord line. But however, when we say lift and drag, lift is normal to the relative wind direction. Okay, so, if you extend this one, then this angle is 90 degrees. So, that is how you define lift. Okay. Now, in the previous lecture we talked about that if you start your tunnel, you start the wing, it is possible that the rearward stagnation point might find a location such as that. However, it is seen that the flow field always looks like this. So, something is happening that is moving this rearward stagnation point in such a way that flow leaves the trailing edge smoothly, and we said that is something which is popularly known as the Kutta condition. That is, you will never have the rearward stagnation point somewhere on the top surface or on the bottom surface, and part of the reason was flow does not like to bend across these very sharp turns that leads to infinite velocities and very large gradients of other flow field parameters. So, in practice we see that whenever a wing starts, a starting vortex is shed, and from Kelvin circulation theorem we argued that some kind of a bound vortex should be established on the wing, and this bound vortex creates a velocity field v theta of the order of the kind of some constant by r, and we will show that when a flow field such as v theta c by r and v radial is 0, this is something which generates something known as a irrotational flow field. So, although you think it is a bound vortex, it is a vorticity should be there, but this is kind of a misnomer to some extent, that is vortex does not always mean vorticity. Okay? Vortex. So, here there is some singularity in the problem, but nonetheless the flow field as a whole, if you neglect that singular point at the source point at r is equal to 0, is irrotational, and we will talk about it in today's lecture, or if we cannot make time today, then in the next lecture. So, this becomes a irrotational flow field. Also I said that far from the wing, or a little bit removed from the wing, your flow can behave in an inviscid manner. So, although you have viscosity, but the gradients of velocity etc. can be small enough to ignore viscosity. So, then in regions such as removed from the wing surface. So, when I say removed from the wing surface, I really mean that removed from the boundary layer of the wing surface. So, in a very thin region, we will talk about what is boundary layer, what is the thickness of a boundary layer, we will talk about what is laminar boundary layer, transitional boundary layer, turbulent boundary layer etc. But you will see it is still a thin region near the wing. In viscous flow fields, if you have inviscid flow, ideal fluid, you do not have any boundary layer, but the moment you switch on viscosity, you will see that near the wing some phenomena happens, because of which you get something called boundary layer. We have not talked about what is this boundary layer, why does it happen, but think of it as a artifact of the viscous flow on the surface of something. So, nonetheless the overall flow field can be considered irrotational even in the presence of a bound vortex. Beyond the wing boundary layer, flow field can be considered inviscid, and of course, if you in most cases the assumption of steady also will hold. Under these assumptions, so irrotational, inviscid, steady, and also incompressible. So, you understand that we have not formally established what is compressibility, what is incompressibility, what is an incompressible flow. So, sometimes your fluid can be compressible, but your flow can be incompressible. Okay. So, we have not talked about this, but think of it as compressibility means can you change the density of your fluid by changing the pressure that is acting on the fluid. In a flow situation, pressure changes happen due to velocity changes. So, if velocity changes are significant, then pressure changes will become significant, and when pressure changes are significant, then density changes can become significant. Okay. So, in high speed flow, where high velocities can come to low velocities near say stagnation points, or in a post shock state, your velocities can change from very high to very low values, and we can show that this large change in velocity can create large changes in pressure, which create large changes in density. So, in those conditions the flow behaves in a compressible manner, but if your flow speeds are low, we will show that below Mach number 0.3 this is what happens, your flow speeds are low. So, it does not matter if you bring it to rest, the change in velocity produces a small change in pressure, which in turn produces a small change in density, which can be ignored. So, then we say below Mach number 0.3 our flow is incompressible. So, somehow if these conditions are satisfied, then we can apply Bernoulli's theorem between a point between 2 points in the flow field. Actually, if all these conditions are satisfied, then Bernoulli's theorem can be applied between any 2 points in the flow field. You do not need to worry about if these things are along a streamline or perpendicular to a streamline or a stream surface etc. But given that all these 4 conditions, okay, A, B, C, D, given all these things hold, then and also of course, the incompressible thing comes in where your flow speeds are less than Mach 3, sorry, less than Mach 0.3, less than Mach 3 is something else, less than Mach 0.3 is where flow behaves in an incompressible manner. Same air, it is a compressible medium, maybe the compressibility is low, but it is still compressible, air is compressible. But in the region below Mach number 0.3, as I said, your changes in velocity are not enough to cause enough changes in pressure to cause enough changes in density. Okay. So, that sequence you have to keep in mind. So, that is why below Mach 0.3 flow can be treated as constant density. So, uniform and steady in terms of density. So, if you have these 4 things being satisfied, then Bernoulli's theorem tells you that you can connect any 2 points, static pressure plus half of density times velocity square. So, you can write this between any 2 points in the flow field. If the flow field is irrotational, inviscid, steady and incompressible, and we will see that it is not a very stiff requirement in real flow fields also, far not just beyond the boundary layer. These 4 assumptions can hold if your the flight speed is satisfies that incompressible range. If I said in previous lectures that if you go into the compressible range, either you have to use some correction, you can still obtain your results from application of this thing, but you have to fit in some compressibility corrections, or you can straight away use the compressible pressure stagnation pressure relationship, which I kind of gave you, P naught into P into 1 plus gamma minus 1 by 2 Mach number square gamma by gamma minus 1, and I said just verify if this is really the form, because I do not have this thing written here. So, sometimes memory can fail. So, just make sure that this exponent is there. So, this equation is valid for your a wide range of Mach numbers. So, this is the more general equation, and it can actually be shown that in the limit of low Mach numbers, this equation really becomes the Bernoulli's equation. Okay. So, it is not like it is something different. Okay. So, in the limit where m tends to 0, this equation actually tends to Bernoulli's equation, which we can show at a later lecture. Okay. So, now what we are discussing right now is, as I said, that you can remember this thing, that is okay, if these 4 conditions are satisfied, then Bernoulli's theorem can be applied between any 2 points in the flow field. We do not have to worry about are the points on the same streamline or the same stream surface, stream tube, etc. But we will see that if your flow field is not irrotational. So, if this condition is violated, this thing will still hold with some restriction. Okay. So, today we will kind of look at that, because it is important. Bernoulli's theorem is is widely used, and you might even use it as a like the back of the envelope calculation before you go into your compressible formulation, etc. So, today we will talk about this thing of applying Bernoulli's theorem if the flow is actually rotational. Also, we will talk about what is this rotational thing. Of course, we can see that it is something that if it is present complicates our life, if it is absent things get simple, but what is the physical notion of this rotational nature? And we said if the flow field has vorticity, it is rotational. If the flow field does not have vorticity, it is irrotational. So, we will talk about that in the as we proceed through this lecture. So, right now to recap once again, in the previous lecture we showed that if a flow field is irrotational, like if all these ABCDs are satisfied, then the addition of static pressure and dynamic pressure between any points. So, here we have a free stream point which we call as the infinity point, and any other point. Okay. So, here we said it is a point A, here is a point B. You can add the static and the dynamic pressure and see that these things become equal if all 4 conditions are satisfied. If all 4 conditions are not satisfied, that is, if you suppose you have a rotational flow field, then also Bernoulli's theorem will apply, as long as you restrict yourself to a streamline. So, if you think that this is your streamline, and we will show why that is the case. So, in this case, suppose it is a rotational flow field for some reason. I mean, I should not really talk about this thing, we should. Okay, so, let us just not get into this one, let us draw the streamline for some other flow field, and I am saying that here the flow field here is rotational. Okay. Maybe I will talk about it in detail in when I come to it, but at this point let me tell you that vorticity has something to do with the rotation of fluid elements. Okay, so, we will see that the rotation of fluid elements are slightly different from the rotation of solid elements, because solid elements will rotate, but not deform when you apply some torque. On the other hand, fluid elements will deform while it is rotating. So, we have a special way of describing the rotation of your fluid elements. So, that we will talk once we are done with the derivation of the Bernoulli's theorem, and we take a look at what is vorticity, what is equation of a streamline, because we will see some of those things will come in. But nonetheless, if the flow field is rotational, unfortunately, why I say unfortunately is if it is irrotational, then you have a lot of simplification in your analysis. However, if the flow field is rotational, and I will not prove it right now, but if you have a flow field say where V theta is C times R instead of C by R. So, here see your V theta was C by R. If you have a flow field like this, you can show that it is a rotational flow field. So, what does rotational mean in that sense? If you take a small chunk of fluid element, you will see that this element is actually exhibiting some kind of angular velocity. On the other hand, you can actually show or see for yourself that here your fluid element will not exhibit a net angular velocity. It will try to rotate in one direction, but then there will be a rotation of the other axis. So, if you think of two mutually perpendicular axes, and we will show these things, you will see that one axis tries to rotate clockwise, the other wants to rotate anti-clockwise. So, overall there is no net rotation, whereas here both the axes would try to rotate in the same direction and your fluid element will rotate. So, that is the rotational word. So, when we say rotational flow field, we really mean that the fluid elements are rotating around their axis, almost like a solid object, but the rotation, because it deforms while it rotates in most cases, the rotation is slightly, so rotation of a fluid element is defined in a slightly different manner, but nonetheless we are saying that in this case, this red flow, your flow is rotational. So, it means that if you do the Ferris wheel test, that is, if you put a crosshair like this, you will see that there is some kind of a rotation that is happening to the crosshair. But again, I think you might like to disregard this thing at this point, because this one is a oversimplified way of looking at it. Let me remove it. Essentially it is something called a vorticity meter. You can take a look at YouTube has videos on this. You put a vorticity meter, whether it will spin or it will not spin. So, in rotational flow field, the vorticity meter will have a angular velocity in some direction. Okay. In a irrotational, the vorticity meter will point in one direction and it will translate, but it will not rotate around its axis. So, here we are saying it is rotational, but it satisfies B, C and D. Okay. It is inviscid, it is steady and it is incompressible. So, in that case it can be shown that pressure say at point 1. So, P 1 plus half rho u 1 square can be shown to be P 2 plus half rho u 2 square. So, as long as they are lying on the same streamline. Similarly, P 3 plus half rho u 3 square can be shown to be equal to P 4 plus half rho u 4 square, but you cannot say P 1 plus half rho u 1 square is equal to P 3 plus half rho u 3 square, because they are not on the same streamline and your flow field is rotational. To understand this, we will look at the derivation of Bernoulli's theorem once again, and this will make complete sense. Also we will see that that the jump in this, so this thing is called the total head, or I mean I think it is really done by the hydraulic engineer. So we have, so in liquid you typically use the rho g h term as well. In aerodynamics and flow of gases, we often ignore the rho g h part. So that way we say P plus half rho u square is equal to constant everywhere if it is if ABCD is satisfied. P plus half rho u square is constant along a streamline and varies from streamline to streamline if B, C, D are satisfied and A is not satisfied. Also when we derive this, when we derived it, if you look at the form of the derivations, you can almost see what will be the change of P plus half rho u square if you move from one streamline to another streamline. Okay. So that can be seen from when we derive the Bernoulli's theorem. So let me go back to the derivation of Bernoulli's theorem. Okay. So for those who have not seen the previous lecture, in the previous lecture we have come to this point where we established that the gradient of P by rho plus V square by 2 plus E times Z is equal to minus So we have in the previous lecture we have derived up to this point, and we said that if the flow field is steady, then this guy becomes 0. If the flow field is irrotational, then this term, okay, this term is known as the vorticity. So given a velocity field, you can find the vorticity field. So if you are given V, you can just run a cross product between this operator and V vector, and you can see the vorticity vector or vorticity distribution if you have the V distribution. And if this one is 0 0 0, 0 I plus 0 j plus 0 k in the Cartesian system, then your flow field is irrotational. However, if it is not 0 vector, then your flow field is rotational. Now if your flow field somehow has turned out to be irrotational, that is vorticity is 0, then this becomes 0. So in that case you get the nicer form of Bernoulli's theorem, where between any two points in the flow field, you do not have to worry about restricting your points to a given streamline. Between any two points in the flow field, you can say that the gradient of this term is 0, and we call it the total head. So gradient of the total head is 0 in any direction. Okay, let me back up a little bit. So this statement says the gradient of the total head is equal to 0. I brought in the idea of a sugar solution in the last lecture, saying that you can think of like the concentration of sugar as the scalar function, and if I say that at a given point the gradient of the concentration of sugar is 0, it means that in any spatial direction, if I move a little bit away from that point, the change in sugar concentration at that due to that change in location is 0. So in the neighborhood of that point, given gradient at that point is 0, It means that if you move a little bit away from that point, the concentration of sugar is still the same. That is why there is no gradient. Gradient means change. So, if I am telling you that there is no gradient of the concentration of sugar in that solution at that point, it means that if you move around that point a little bit, there is no change in the concentration of sugar at that new point. Now, similarly, if you think of the gradient of the summation of p by rho, v square by 2 g z, and if I say that that the gradient is 0, it means 0 I, 0 j, 0 k, that is in any direction you move, there is no change, so there is no gradient. It means then that at the new point also your p by rho plus v square by 2 plus g z, the summation will stay the same. Things can vary individually, your p and your v and your z can vary, but the summation of those things, the p by rho plus v square by 2 plus g times z, that whole thing will stay the same as you move from point to point. So, that is what is meant by that gradient is 0. Now, let us bring in, so this thing, if this thing happens, then if this holds, so if one holds, then we have p by rho plus v square by 2 plus g times z is equal to constant throughout the flow field. You do not have to worry about streamlines and all those things, it is just constant throughout the any 2 points in the flow field, as long as those A B C D conditions are satisfied, then the gradient is 0 at every point, and then it means that you start from one point and you can move to the never, 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 and that way you can go to any point, and you can see that this term is constant. Popularly we say p plus half rho v square or half rho u square. I mean that u v is essentially the net velocity, okay, net velocity in the sense, so you might have v composed of u, v, w, etc., but we are talking about this net velocity, okay, not the components small u, small v, small w. So, think of it as small u, small v, small w, and the net as capital V or capital U. So, here we have used capital V plus rho g z is equal to constant. And I said in aerospace problems or aerodynamics problems, we often ignore the gravity term because that is a small contribution. Okay. So, up to this more or less we had seen our in the previous lecture. So, today I want to bring in what happens if this term is not 0. Okay. So, let me change the color slightly. So, today we will consider what happens if we have a rotational flow field, but other conditions are satisfied, because see, if it is not incompressible, then this form will not happen. We could bring this thing inside that gradient operator only by saying that density was constant. Okay. So, now we are relaxing the restriction imposed by A, but B, C, D, etc. are there. So, this time I am saying it is steady, but it is rotational. So, this term is not vanishing. Okay. So, here you just have to think of your vector calculus or vector geometry. You have to recollect your vector in high school. We do basic vectors. So, here essentially you just have to recollect some of those basic lessons in vectors that you have taken. So, this one says that, so this is vorticity or rotationality in some sense. We will show that vorticity is related to the angular velocity of fluid parcels. At this point just remember this. So, that is where that rotationality comes in, the connection between vorticity and rotationalness of the flow field. So, here we are saying that if this is not 0, then the gradient is no longer 0. So, you see that there is some gradient now. So, there is some gradient because this right hand side is not becoming 0. So, there is some gradient now. So, you cannot just say that these things are the same. but as I have already mentioned that in the special case of looking at gradient along the streamline, I mean I have not talked about what is a streamline properly yet, but I will talk about that thing momentarily. If you think of the gradient along the streamline, you will see that the component of gradient in the direction of the streamline is actually 0. So, although I am saying that in this case looking at this one, I am struck with the thing that now the gradient is not equal to 0, but I am saying in the special case of, so now you have a gradient vector, some I, some j, some k vector is there. But if you take the component of that gradient in some special direction and it becomes 0, it means your gradient overall is not 0, but if you consider that particular direction, then the gradient is 0. So, what does that mean? It means that if gradient is 0 along that direction, although gradient is not 0 in general. So, if the right hand side, if this were 0, then my gradient is 0, I do not need to worry about which direction or any direction is 0. But in this case I am saying the gradient is not 0, because we somehow the flow field, the that particular flow field that we are discussing has rotational behavior. So, then the gradient of these gradient of the total head is not 0, there is something, but remember this is a vector, okay, this is a vector. So, a vector might still have a 0 component in some particular direction, okay, the component of a vector in that direction. Now, if it can be shown that if you are looking at the direction of the streamline, then the component of gradient along the streamline is 0. So, which kind of means that there is no gradient in this total head if you move along a streamline. So, how is that thing established? That thing is established pretty much by looking at the direction of this vector. So, let us quickly take a small detour and look at your the basic cross product. So, suppose you are looking at C, which is a cross product of A and B. What this means is, if you draw, or rather let us draw A like this, B like this, then C vector is something that is perpendicular to both A and B, and the product is given by the magnitudes of A and B into sine of the angle between them. So, C vector so if you look at the product of these two, so this is the velocity vector and this is the curl of the velocity vector. So, the product of these two will be normal to the velocity vector, okay, the cross product between this vector and this vector, the resultant vector will be normal to each of these two vectors. So, if the resultant vector is normal to the v vector, that means it is normal to the streamline direction, because your streamline. So, what is a streamline? Let us quickly, it is interesting that to understand drag, you see that we have to understand all these things, and that is where the utility of these tools are come into play. So, instead of learning this thing as Bernoulli's theorem and this and that, here we are learning all these things because we are trying to process how drag is generated on a wing. Okay. So, the overarching goal is to understand drag, and these are the like the basic modules that come into play in understanding drag. So, here I am saying that the cross product between this vector and this vector will be normal to the velocity vector. Now, the streamline, so if you suppose in a flow field, these are the instantaneous velocity vectors. You see, I am trying to think of the resultant streamline, so that it does not become too difficult for me to draw. So, suppose these are the instantaneous velocity vectors in a flow field. So, you can, there are many experimental techniques that can give you velocity vectors all throughout a flow field. For example, popularly there is something called PIV. Since this is an introductory course in aerodynamics, nothing is beyond the curriculum in some sense, because the purpose of this course is to introduce you to everything that is there in aerodynamics. Of course, we have a limitation of the class lectures and the like the semester time, etc. So, we cannot of course do justice to the what we have to what we would like to present to you, but as and when things are come in, we should still try to learn a little bit of these things. So, there is something called particle image, some people say imaging, particle imaging velocimetry, or particle image velocimetry. As you understand, velocimetry, as you understand, it's something to do with the velocity. And what happens is, suppose you have a flow field and you seed the flow field with some particles, typically glass beads or something, very small, very light particles, and then you shine a laser sheet through the fluid. What happens is, when your glass particles, or I mean, there are various kinds of seeding, glass bubbles are just one of them. It depends on if you are doing a reacting flow measurement of velocities at various points in a given instant of time. Of course, glass bubbles will not work, say some oxides of calcium or some other particles that are stable at high temperatures would be required. But nonetheless, the principle of PIV is, you seed a flow field with particles, then you shine a laser sheet, so your particles become visible, and then you take a picture. You take a picture at 2 successive intervals. So, what will happen is, in image 1, for example, in picture 1, suppose we are trying to study the flow around a cylinder. Okay. So, in picture 1, the laser sheet has rendered these particles visible, and you have a picture like that. Okay. So, particles are at that location. Then at a instant, so if this is t, then at an instant of time, so this one is say t plus delta t, and a part of running a PIV measurement, particle imaging velocimetry, particle image velocimetry measurement, is to find the right size of these particles. You would like them to be small, because small particles follow the flow properly. If you have large particles, of course, you understand that they will not follow the flow faithfully. If you have a, say if you have a tennis ball like particle, and you have a flow that is bending sharply and twisting, turning, your tennis ball may not really follow the flow faithfully. So, you want particles that are really small, so that they follow the flow faithfully, they can come to the equilibrium with the local flow speed quickly, etc. But then again, depending on the size of these seeding particles, so these particles are not really part of the flow field. You put the particles, because otherwise laser sheet will not make anything visible, air has nothing. So, you put some particles, so that the laser beam can make these particles visible, and then by looking at the position of the particles. So, say time t, my particles are here, in time t plus dt, my particles move there. Okay. So, just think of the blue location as my this time t plus dt particles. Then, since we do not know which particle moved where, some pattern recognition kind of thing is done, and it you can, the analysis tells you that it seems that these particles, let us see, undo. Okay. So, a pattern recognition kind of algorithm, which is, you will see it is called cross correlation. There is a cross correlation technique by which you can figure out that these red particles in this region in the first picture on the average moved to this region. So, then this gives you the velocity vector, or rather it gives you the displacement vector. Okay, why did it remove it? So, suppose you have some red particles from frame 1, and from that analysis. So, I am not talking about that analysis, somehow suppose there is an analysis that can tell you that these particles move to that region. So, then you get the displacement vector, okay, displacement vector, and you know that time interval between the two snapshots. So, you can get the velocity vector. Similarly, suppose your cross correlation. So, it is based on this thing called cross correlation algorithm. It is quite a straightforward thing, and MATLAB, for example, has a function to run your cross correlation. I think it is xcore or xcore 2 or something like that. So, for example, here suppose your particles in this region at time t, time, the initial time, your analysis, your cross correlation algorithm is telling you that these particles on the average have moved to this location. So, then your displacement here is like this. Okay, so, it was northeast displacement, here now you have southeast displacement. So, then after this whole PIV analysis, you will get your result set will look like this. That is your domain, that is your cylinder, and you get velocity is like this here, velocity is like that there. Okay, so, this is like the practical way in which we get a velocity field. So, then we say that at time t, this is my velocity field. So, now if I go in and close, find the other velocities, perhaps something like this will come out. Okay, so, your PIV will give you all this information. Okay, of course, you cannot have the velocity vectors are just small straight arrows. Now, what is a streamline? So, if I have the velocity vectors at a given instant of time in a flow field, streamlines are nothing but hypothetical lines such that the tangent at any location on the streamline gives you the direction of the local velocity vector. Okay, so, you can imagine that I can draw something like, or something like, so those things will become streamlines. Okay, but streamline is a theoretical concept. There is nothing like a streamline in a real flow. It means that if I take say this point, then this will be the direction of my velocity vector. If I take this point, then this is the direction of my velocity vector. So, you start from the velocity vectors, you fit in a curve such that at any location the local tangent is along the velocity vector, then that is called the streamline. So, in this case you can think of it like this, and intermediate points depend on the velocity vectors. I am not drawing all the velocity vectors. Okay, so, these things are, let us assume that there are the velocity vectors are such that that is the direction of the streamline. So, you see at this point the local tangent is along this velocity vector, at this point the local tangent is along this velocity vector, at this point that local tangent is along this velocity vector, at this point the local tangent is along this velocity vector. So, then your red curve is the streamline or the streamline direction. Now, see what is happening here. So, this thing is perpendicular to the velocity vector, hence it is perpendicular to the streamline direction as well. Okay. So, this gradient vector is actually perpendicular to the streamline direction. So, if it is perpendicular to the streamline direction, then if you take a component of this thing along the streamline, then it is 0, there is no contribution of that gradient vector along the streamline direction. So, in that case, this thing has no gradient, because see the gradient, this whole thing is at right angles to the velocity vector or right angles to the local streamline direction. So, there is, if you, what is the component along the streamline direction then? If a vector is perpendicular to another vector, it means that it has no component along that, none of these vectors have a component along each other. So, then we can say that since the direction of this one is normal to the velocity vector, hence normal to the streamline direction, that means this thing has no gradient along the streamline direction. Whatever it has normal to the streamline direction. So, along the streamline direction it has no gradient, which in turn means your p by rho plus v square by 2 plus g z is constant, no gradient along the streamline direction, means it is not changing along the streamline direction. So, then p plus, so along the streamline p plus half rho u square is equal to constant along the streamline, okay, constant along streamline. If the flow field is irrotational, you can, this is constant all at any 2 points, does not matter where you choose the points. If the flow field is rotational, then we are showing that there is a gradient, but the component of this gradient along the streamline direction is 0. So, there is no gradient if you choose the special case of the streamline direction. Okay. So, that is where a little bit of restriction comes in, but Bernoulli's theorem is still valid. You can apply it, but there is a restriction. So, what we say is, let us take the dot product of this gradient. So, we say that gradient of p by rho plus v square by 2 plus g z, whatever we get here, take a dot product with the local streamline direction. And that can be shown to be 0, because this vector is normal to the streamline direction. So, that is just another way of saying that the gradient along the streamline direction is 0. So, there is no change along the streamline direction. So, that total head stays conserved along the streamline direction. What happens normal to the streamline direction? This is the change that is the gradient normal to the streamline direction. So, the change in head can be obtained from this value itself, from one streamline to another streamline, because this gives you the component normal to the streamline direction. Okay. So, you have a change, and that is what the amount is. So, along the streamline no change, perpendicular to the streamline this is the amount of change. Okay. So, we will continue in the next class. We will talk about what is vorticity, we will look at some examples, etc., and we will relate that rotational nature to vorticity, so that you understand on a physical sense what is this irrotational, what is vorticity, etc. Thank you very much.